Yes, so welcome everyone. Thanks for coming. Thanks for listening. If you're listening to these things or watching online, this is the second part of Athar Abdul-Qader's talk on representations of lattices. Yes, so go ahead.
Okay. And let me get this right. Thank you, Raman. And so I'm going to start with some reminders of some definitions and results that we talked about last time. But mostly last time I went through, my goal was to kind of try and motivate these definitions in the context of giving a particular example where we're trying to construct an elementary extension with a given interstructure lattice. And in that case, it was B2. And I'm going to continue on that example today, but now I'm going to analyze it more from the perspective of the ranked of a ranked lattice. So let's start with a reminder of some of these definitions. So suppose you have a set X and a lattice L. The set EQ of X is the lattice of equivalence relations on X. Its top element is the trivial equivalence relation X cross X, right, where every element of X is related to every other element, and the bottom element denoted 0 is the discrete relation, the relation where these equivalence classes are singletons. Alpha is a representation, or essentially a representation is a one-to-one function from a lattice L to this to a set of equivalence relations, or to the lattice of equivalence relations on X, where alpha of 0 is the top element. In other words, it's the trivial relation. Alpha of 1 is the bottom element, and i.e. the discrete relation, and alpha joins into meets. Okay. The way I think of this is if you think about the ordering, if X is below Y in the lattice, then alpha of Y should refine alpha of X. That's how I sort of, so alpha is a representation. If it sends the top element to the trivial, or the bottom element to the trivial relation, the top element is discrete, and then we refine as we go up. Okay. Suppose we have a representation on a set X. If we have a subset Y of X, oh, this is where I hope Jim was here last week. So maybe I can ask Jim, how do you read this? I read this as alpha bar Y.
Well, I don't read it. I only write it.
Right, you just write it.
Yeah.
Right. So I read this as alpha bar Y, and
I guess restricted to or
okay,
something.
yeah, that's what I was unsure. Do we read it as a restriction? So alpha restricted to Y is the representation on L defined onto the set onto the equivalence relations on Y, defined by essentially taking each equivalence relation alpha of R and restricting it to Y. So intersecting it with Y squared. An equivalence relation theta is canonical for a representation alpha if there's some R where theta is exactly equal to alpha 1, right? And the idea we're going to have is we're going to take a representation alpha and equivalence relation theta, and we're going to find some subset where theta is canonical for alpha restricted to Y. All right, and alpha has the 0 CPP property, or zero canonical. Alpha is 0 CPP, or has this 0 canonical partition property if for each R, alpha of R does not have exactly 2 classes. And we saw last time that this property was important when we were trying to show that a particular type we were generating was going to be complete. Okay. Alpha is n plus 1 CPP if whenever you have an equivalence relation theta, you can find a subset of X where alpha restricted to Y is n CPP and theta is canonical for alpha restricted to Y. Okay. And then some more definitions. we can relativize all these definitions. We can relativize the previous definitions, both in terms of the definition of a representation. We can relativize that to a model of PA. So an M representation is a representation where alpha and the set X are both M definable, where M is some model of PA. For a definable set X, we can look at the lattice of M definable equivalence relations on X. I didn't say this here, but even this notion of CPP representation can be relativized into a model PA. In other words, if L is a finite lattice, there's a formula that says essentially a formula CPP of L and X that says L has a X CPP representation. And so you can sort of you can kind of formalize that within PA. A family.
Yeah, incidentally, that I think works only for M finite representations.
Yeah. Yeah, makes sense. C is an M correct. A family of representations is called M correct, or is called an M correct set of representations. If I had this typo last time and I didn't fix that. I thought I caught all the typos. If C, so delete this each. If C is a non-empty set of 0 CPP representations, M representation, and whenever you have some representation in C and some definable equivalence relation theta, you can find some restriction of alpha where theta is canonical for that alpha bar y. Okay. And again, we saw last time essentially that this property was really needed when we try and build this particular type, that we build a type and we're trying to control all the M definable functions or all the Skolem terms, however you want to think about it. And when I say we want to control it, we want to make it so that each one of these Skolem terms or each one of these M definable functions defines essentially a generator on one of the interstructures in the lattice. Okay. So and I'll recall this construction that we had with of a extension whose interstructure lattice is exactly the lattice B2, and I realized I didn't put in the drawing of B2, so let me draw that in here. So B2 is this lattice. B2 is this lattice with a bottom element, and I'll label this A and label this B, 0, 1. A bottom element 0, a top element 1, and then two incomparable elements A and B in between. Okay. And the representation, so we're gonna take the set X to be the set of codes of pairs X, Y, where X is less than Y, and we define a representation of B2 on the set X. Again, 0 and 1 are defined by are given to us by definition. Alpha of 0 has to be trivial. Alpha of 1 has to be discrete. And we make alpha of A to be essentially the representation that makes two pairs equivalent if their first coordinates are the same. And alpha of B is going to be the representation that makes two pairs equivalent if their second coordinates are the same. And so you can see that essentially this, it's an exercise to check that this satisfies this definition over here, that, right, if you look at alpha, if X and Y are A and B, and you look at A join B, that's 1. So you want to make sure that alpha of A intersect alpha of B is alpha of 1, which is discrete. And so if you check that, if two things are equivalent according to alpha of A and according to alpha of B, then they're, of course, the same exact ordered pair. And so how does this representation help us build a type? we enumerate the m definable equivalence relations on X as theta 0, theta 1, etc. I'm assuming m is countable here. We start with x0 being the set X, and then for each I, we find some subset of xi so that alpha bar xi plus 1 is isomorphic to alpha. And I'm realizing I may have left out that definition. I thought I copied all of them over. I apologize. Essentially, this means that there is a bijection between x and xi plus 1 that commutes with the equivalence relations, essentially, with each of these. And so you want to find this large set xi plus 1 and make sure that theta I is canonical for alpha restricted to that xi plus 1. This sequence then x0, x1, etc. will generate will generate this type P of x in this way. And I think Roman went over this, mentioned described these as essentially definable ultra powers. And if you have an element that realizes this P of x, then we went over this a little bit last time of how we can ensure that this interstructure lattice is exactly going to be B2. And I talked about this a little bit last time. I'll just direct you to the recording for that. But I can answer questions if there are as they come up. And my goal in going over this was to try and motivate this theorem from Jim, and that says if you have an elementary extension whose interstructure lattice is isomorphic to L, then you have this kind of M-correct set of representations of L. And if you have a model that's countable and it has an M-correct set of representations, then you can kind of do what we just did to find an elementary extension which has exactly this interstructure lattice.
Athar,
Yes.
Yeah, Athar, you on your previous slide,
Mhm.
You
Right.
said that alpha restricted to xi plus 1 was isomorphic to alpha.
Yes.
So I'm not sure about that.
I mean, I think you can do this in this case for B2 because of canonical Ramsey's theorem. Is that not right?
I think it works for B2, but
Yes.
it doesn't work for that theorem that you.
No. So this is not this was just for that particular example.
Oh,
This is
okay.
isomorphic.
All right.
The theorem is more general, as Jim points out, that you don't, this M-correct set of representations, so let me go back to the definition of this M-correct set of representations. It's just any set, and there's no you know, so if I were to say something about this, in our example, this set is going to be the set of all alpha bar x such that, or let me call this alpha bar y, such that alpha bar y is isomorphic to alpha, let's say. And this and this is going to be an M-correct set of representations because of kind of because of kind of this canonical Ramsey's theorem.
So
this is not true in general. This is only true because of this lattice B2 has very nice like combinatorial properties. Sorry, go ahead, Jim.
Right, but that's only for end extensions then.
Yes, that I'm going to say something about generating
but the theorem that you have on the next page doesn't say end extension, I think.
No. Again, I'm gonna show your more general your theorem about ranked lattices in a bit, which will hopefully do this. This was just kind of a warm-up example that I wanted to do last week. Okay. So anyway, this is this is what Jim's saying, that this is a very particular example which generates an end extension, and I'll say a little bit about why. But this M-correct set of representations is a very general notion. It's just saying you have any set which has lots of representations in it, and each one you can refine for any theta, right? And if you have this, then you can start with any alpha, and you can start with x0 being any of these x's that you have for one of these alphas. I meant to just highlight that x, and then do kind of the same process. And since alpha bar y is going to be in C and theta is going to be canonical for that, you can kind of do the same kind of argument that we did last week to generate B2, except we don't need, we don't need this sort of isomorphism. We don't need quite as strong the sort of combinatorial properties that I'm saying here. Okay. I think I heard someone else besides Jim.
I was going to ask about the theorem. The second part of it.
Yes.
Number two, so you don't want to say anything specific about what this extension then is. Doesn't have to be, well, in some cases it cannot be an end extension.
Yes.
So, but is the theorem and the way it's proved that you always produce a cofinal extension? Because then you need also M to be non-standard.
I have to remember. I have to remember if
I think you want M to be non-standard here.
yeah, I
I
think
think so.
I meant to say non-standard. I'm trying to remember if I
And
have it.
countable, maybe.
I think I have countable here, but
It's countable
Oh,
already.
in number 2.
Right.
yeah, in number 2, I have countable. I don't think you need. Did I lose? Yeah, I've lost my screen. Sorry, I lost my screen for a second. I might need non-standard here. I'm not. I have to go back and check that. All right. So what I want to talk about today is to examine the construction that we did and see what kind of extension we end up getting. And as Jim points out, this construction, we end up getting an end extension. And I want to kind of think about why that is, and also what the interstructures are, and we'll if you, I mentioned this, Rez was here last time and asked me which one ends up being, does M of A and does M of B end up being, does one of them end up being an end extension, one of them end up being cofinal or something like that, and which one? And so I wanted to analyze that a little bit more and to try and understand what you can do to actually ensure a certain a certain ranking of your lattice. Okay, so to remind everyone, this is a definition that Roman put up a couple weeks ago. A ranked lattice is a lattice L equipped with this function rho, which and this is the ranking function. And essentially, this ranking function has to be non-decreasing, and it has to be kind of a linear ordering. And idempotent. And so you can look at the rank set. The rank set has to be a linear order. Is one of the things that you get here. The only ranking the only ranking we will care about is the ranking we get from Geifman's splitting theorem. So if you take a model at K that's in the interstructure lattice, you use Geifman's splitting theorem to find some extension K bar where K is cofinal in K bar and is an initial segment of N, not necessarily proper in either direction. And then the rank of K is going to be defined as this K bar. And so that's what I wanted to mention today, which is what is this rank set for the extension that we constructed. And so we had this this was the sort of we had a model M, we generated a type where C realized this type, and then we kind of, and I didn't mention this, but C we're gonna be we're going to let the projection on the first coordinate of C to be A and the projection on the second coordinate to be B, kind of suggestively. And so then M of A and M of B are the other interstructures. And what is the rank set? And so I'm gonna go through this first. So let me just draw out the picture and or draw out the model. So M is going to be sort of the ground model. A is going to be somewhere up here, and B is going to be somewhere up here, and this is going to be M. This big picture model is going to be M of C, right? So C is going to be in. Sorry, C is going to be in this sort of larger. C is going to be somewhere in here.
Right. Athar, so can I just make a small comment?
Yes.
Because when in my lectures I use this example as well. So that was this to explicate how Geisman minimal types are being used.
Mm-hmm.
So there's this canonical way of making this type of an extension.
Yeah.
So this other method that sort of and for that method you don't need M to be countable. It's just something that works always. And this is this particular feature of this one technique that's great in one thing, but doesn't really produce much more than that.
Yeah. Okay. So I wanted to go through, like I did last week, to kind of talk through each of these individual extensions, and essentially, here's my drawing. Let me say a little bit more about this drawing. So essentially, what I'm saying here is that M here is essentially the initial segment. Then M of A is the next initial segment, and so it's going to look like M is an initial segment of M of A, which is going to be an initial segment of M of C. And M of B is going to be what Roman mentioned. He had this kind of in his talk earlier. M of B is going to be the stuff that's up here, the stuff that's down here, and so M of B is going to be cofinal in M of C. And so I want to claim that this. So I made this kind of informal comment last time that the type knows this. That the type knows that M of the type of C knows that knows that these are the interstructures, and moreover, I want to claim that the type of C knows that, or somehow when we were building this type, we kind of encoded that M of A was going to be the sort of an end extension of M, and M of B was going to be cofinal in M of C. Okay. So let me switch over to yeah, so let me switch over to my to a notebook so I can make each of these arguments. So let me switch over here and draw this out. So first I want to say that M is the M of A is an end extension of M. And so why is this? So let M be an M, and suppose that M of C thinks that let me do this first. M of C is an end extension. The top model that we had built. And so again, we're gonna think of this as think of the B2 as this interstructure lattice. So suppose there's some term T where or M definable function where T of C is below some element of M. And so I'm gonna remind you. So how do we use the fact that we built this type very specifically and we made it we made this sort of the equivalence relations canonical and all that. This T of X induces an equivalence relation, and I mentioned this last time. How I explained this last time, so I'll repeat it now. Theta defined by x is equivalent to y if and only if t of x is equal to t of y. Moreover, this equivalence relation theta we can assume to be canonical for some xn. So assume it's canonical on xn. Okay. And it has at most m many classes, right? And it has at most m many classes. But if you look at our definitions of alpha of A, alpha of B, and alpha of 1, each had m infinitely many classes, right? They didn't have boundedly many classes. And so it would be impossible for a theta to be equal to one of these on xn. So it must be alpha of 0. Okay. And so what does that mean? Alpha of 0 is the trivial relation. So that means that theta is trivial. Everything is equivalent to everything else. And if everything is equivalent to everything else, that means just t of x and t of y are always equal. That means t is constant on, so t restricted to xn is constant. Okay. Good. Any questions? Okay. Next part is that, so we have, again, with the next part is I'm going to claim that exactly one of m of A and m of B has to be cofinal in m of C. Okay. This follows from some of the properties about rankings and some of these the Glass and Geifman properties that were mentioned. So let me mention this briefly. So exactly one of m of A, m of B must be cofinal in the top model m of C. And so, well, why couldn't both, right? If both were cofinal, then the Blass condition would imply that m of A intersect m of B would also be cofinal. But this is m, and we just said it's not. We just said it's an initial segment. So they can't both be cofinal. Okay. They can't both be end extensions. So if neither is cofinal, because in that case the rank set would not be linear or ordered, right? The rank set would contain both m of A and m of B. So this is from the definition of a rank. Okay. Any questions about that?
So how about mixed?
Right. Okay. So can either one of these be mixed? No, because these are minimal extensions. So m could be mixed. We'll say something about that. In this case, m is not mixed. M is m of C is an end extension of m. But since m of A has nothing in between it and m of C, it has otherwise you would close under initial segments and then you'd get something that's cofinal and
Right.
in between. Right. So a minimal extension has to be either end extension or cofinal extension because of Geifman splitting. Good. Any question? Okay, great. What else do I want to do here? Oh, so let me switch back over. So okay. And so I think I just summarized this. So this is exactly what I just said to Roman's question. Because MFC is a minimal extension of each of those, each one has to be a cofinal end extension, and then I'm summarizing exactly one must be cofinal. If they were both, then n would also be cofinal, and if they were both end extensions, essentially that can't be because of the definition of ranking. But another argument you could give is you just see which one is bigger, and then so if they're both end extensions, then the smaller one would be in the bigger model as well. But that's not true because they're incomparable. Okay. So that still leaves the question, okay, what exactly is the rank set? And I claim this is the rank set, M of A, and M of C. Okay, and so what is that? Why is that? Well, what you get, since I said we started with this set of pairs where X and Y, of X and Y, where X is less than Y. And so so right away, looking at the type of C, this projection on the first coordinate is less than this projection on the second coordinate. This is a true statement about C. The projection on the first coordinate is less than the projection of the second coordinate. It is a true statement about every element of the set X, and so this is in the type of C. It's in the type that we defined, and therefore C will think that A is less, or M of C will think that A is less than B. And that right away tells you that M of A has to be M of C has to be an end extension of M of A, and M of B has to be cofinal. Okay. So that tells us, okay, the rank set has to be M, M of A, and M of C. Right? How did the representation alpha tell us this? How did we code that into this representation? And this is where I'm trying to build up to Jim's results about representations of ranked lattices. Okay. The idea is for each pair of elements R and S, where R is less than S in the lattice, we look at, I mentioned that alpha of S is going to refine alpha of R. So we want to look at how the alpha of R classes split into alpha of S class. Okay. And so think about M, this is maybe a good time to remind you what are these alpha of B classes and alpha of A classes, right? So the alpha of A classes are the ones where the first coordinate is constant and the second coordinate varies, right? So an example of alpha of A class could be the set of all like 0, y for any y for any y greater than 0 in the model. So if you look at the alpha of A classes, that alpha of A class is unboundedly large, right? And so if you look at how it splits into alpha of 1 classes, that has unbounded, like the alpha of 1 classes are singletons, so that has unboundedly many alpha of 1, that alpha of A class splits into unboundedly many alpha of 1 class. In fact, every alpha of A class has that property. But if you look at an alpha B class, an alpha of B class is the equivalence relation for alpha B is equality on the second coordinate. So you fix some y, and you look at the class will be the set of x, y, where x is less than that y, right? And so for whatever that y is, that's the size of that class. That each of these alpha of B classes is M bounded. Okay, and it will split into that many alpha of it'll split into M boundedly many alpha of 1 classes, M finitely many, right? And so that's this idea of this class, this alpha of B class splitting into M boundedly many alpha of 1 classes is somehow telling us something about this being a cofinal extension, and this alpha of A class splitting into infinitely many alpha of 1 classes is saying something about this this extension MA to MC being an end extension. And then the alpha of 0 class that's unique, that splits into unboundedly many alpha of A classes. There's infinitely many alpha of A classes. Yeah. Okay, so that's the idea. And again, I'll mention the theorem. Well, I'll mention the theorem in a couple more slides. for B2, there's actually a lot of different possibilities. In general, there might not be as many, and this is something that I think is interesting and is worth thinking about. But for finite distributive lattices, the answer is somewhat known, and it's in the book. I think it's in Jim and Roman's book on how to realize all possible rank sets. But for B2, I showed that we have the rank set that has the ranking that has 0, A, and 1 as a rank set can be realized, and that was my construction from last time and what we looked at just now. What other rank sets could work? And essentially, well, A and B are essentially isomorphic. So not, if I put this, it's kind of the same construction. It's so I'm not gonna consider any of the possibilities where B is in the rank set, because it's kind of symmetric. This can be realized. This 0, B, and 1 can also be realized, and essentially just switch around the inequality that I had, right? Have X greater than Y instead, and then you'll get the same kind of thing. Okay. What else? This is a linear. It's not letting me erase what I thought I could erase. This is a linearly ordered set, and that. So this this could work. Okay. This is a linear ordered set that could be a rank set. What about this one? This can't be a rank set. 0 and 1. I guess I should have confirmed. Can everyone see the drawings that I'm doing?
I can.
Okay, good. It's showing up both on my iPad and on my screen, so I thought we're good, but I should have made sure. This cannot be a rank set because of the argument I gave, and I'm gonna mention again, that said that M of A and M of B both can't be cofinal if the ground model is an initial segment. Because this is saying M is going to be an end extension of M of C, but M of A and M of B are both going to be cofinal. And that can't happen because of Blass's theorem. Okay. Or Blass's, the Blass property. So what other rank sets could work? Well, I'll tell you all of them. So this is, yeah. We cannot have both M of A and M of B be end extensions. So in other words, M of A and M of B both cannot be in the rank set. So at least one has to be a cofinal. So let's assume that M of B is cofinal, which means the rank of B is going to be the top model. So the rank of M of B is going to be N. I'm sorry, I think I talked over someone. Was there a question or a comment? Okay. In that case, so again, the possible rank sets are just the top model, and that would be if you're realizing a cofinal extension. What we just did, which was M of A, and N, and that would be if M of A is an end extension of M, and N is an end extension of M of A. And this last one, which we realized this one. I'll say about number 1, this is a general result of Jim's that if and again I'll mention this at some point, I think if a finite lattice can be realized and M is non-standard, then then it can be, that finite lattice can be realized as in a cofinal extension, right? As the interstructure lattice of a cofinal extension. So what about this one? This would be an example of a mixed extension where M is cofinal in M of A, and N is an end extension of M of A. And so can each of these be realized? Well, one definitely can be realized by general results of Jim, that anything that can be realized in a cofinal extension. 2, we just did.
I thought, sorry,
Yes.
about 1. So doesn't it follow from the fact that every countable model has a minimal cofinal extension? So if you do it twice, you will get V2. Isn't this right? Or
How do you know that you didn't end up with the lattice 3? Or the lattice,
I see.
or the lattice M3 for that matter, right? There's a lot of, if you do
I see.
two
Right.
yeah.
So this will be more like getting M3.
Yeah, so
Okay. Right.
minimal, you want a minimal extension that has, okay. I mean, it's more like trying to find a minimal,
How about
Uh,
super minimal followed by super minimal?
that will give you 3.
They will give me 3. All right.
They'll give you
Right,
exactly
right.
the lattice 3 and
Right.
yeah. For B2, this really just follows from the fact that that you have n CPP representations for every. I mean, it follows from Jim's general results that if you realize any finite lattice in any extension, then you can realize it in a cofinal extension, and that's essentially because the notion of these CPP representations can be formalized, and so you can overspell to get some sort of non-standard CPP, like non-X CPP representation. And so you get some finite representation or M finite representation that has has this canonical partition property at a non-standard level. All right. Can this one be realized? And it essentially it can be, again, if you're starting with a non-standard model, you do the exact same representation, but you just put a bound on this X, and that same representation can work. You won't get isomorphism in this case, but you can still get large, non-standardly large representations where each alpha of A will have non-standardly many classes, and there's an alpha of A class that's unbounded, and you can make each theta canonical. And kind of with that same construction, you can make sure that this is cofinal in that M is cofinal in M of A, and N is an end extension of M of A. Okay. And then you get this interesting property that M of B is an end extension of M, and N is a cofinal extension of M of B. Okay. So the point is that essentially somehow this representation tells you something about this ranking, so that you're going to realize, and it tells you something because of what I said here, that if we look at how each alpha of R class splits into different alpha of S classes, and so in this case, you look at how does the alpha of A classes split into alpha of 1 classes. Well, there's non-standard, there's M many alpha of A classes here, and then for each xn there'll be non-standardly many alpha of A classes, and so they'll so I guess to put it this way, the unique alpha of 0 class, which is the one at the bottom, is going to split into finitely many or m finitely many alpha of A classes. If you take one of these alpha of A classes, if you fix an x here that's below m, there's infinitely many or unboundedly many y that are in this x, where xy is in this x0. And so this alpha of A class is going to be unbounded. And that means that this alpha of A class is going to split into unboundedly many alpha of 1 classes. And so if you look at how the alpha of 0 classes split into alpha of A classes, how the alpha of A classes split into alpha of 1 classes, etc., that tells you something about these being this being cofinal and this being an end extension. And that leads me to Jim's definitions and results. And let me see if I guess I didn't mention. So I need to make a slight change to the presentation, but I'll just do it out loud. So suppose you have a model and a finite ranked lattice. If you have a definable set and some definable equivalence relation theta on this set A, then we say a set of classes is M bounded if there's a bounded definable set in M that intersects each one of these classes, each one of these theta classes. And an M representation of L row of a ranked lattice is an M representation of L. So again, a representation of L on a definable set A, where this representation and the set A are both definable. And whenever R is below S is below the ranking of the rank of R. Okay, so what does this mean? This is going to say that the Rth model is going to be cofinal in the Sth model, right? M of R is going to be cofinal in M of S. If you think like that. So in this example, you might think of 0 versus A, right? M of 0 is going to be cofinal in M of A. Okay. If every alpha of R class is the union of an M bounded set of alpha of S classes. And that's the main thing that makes you able to control which of the interstructures end up being cofinal, which of the extensions end up being cofinal, which end up being end extensions. I guess I should say a model ends up being an end extension here. So a model ends up being an initial segment if it is its own rank, right? If the rank of R is equal to itself, right? So if you want, so this tells you something about when if you have two models in the interstructures, when one of them is cofinal in another. So if you wanted to say, okay, it's when if, right? Well, I guess let me how am I say this? If I want to say that K1 is an K2 is an end extension of K1, then you would need this to not happen. In other words, you need some alpha of R class that splits into an unbounded set of alpha of S classes. Or yeah, I guess that's the way to say it. And then an M correct set of representations of a ranked lattice is an M correct set of representations of rank, right? Exactly what sort of the generalization of we had before. And so the theorem is essentially the theorem from before. Again, I missed the word non-standard here. I think the word non-standard should be there. If you have a model M and an extension N where the ranked lattice is isomorphic to L with this ranking row, then you can get this M correct set of representations. And vice versa, if you have a countable non-standard model with an M correct set of representations, then you can realize this ranked lattice in an elementary extension. And so this property is what we needed to ensure we get a particular ranked lattice. Okay. Any questions? So let me say for a few minutes a little bit about this pentagon lattice. So this is the pentagon lattice N5. And so the question that I want to think about and I want to mention Jim's result on is which rank sets can be realized. And so, okay, first of all, a row of C is not going to be C. So the rank of C can't be itself. And that means that the rank of C has to be 1. And so in other words, if we think of this being, you know, some interstructure lattice, we think of this being some interstructure lattice, M of C, M of B, M of A, and M. If it's going to satisfy the Geifman condition, the Geifman condition said that if x is less than y and it's less than x join z, and z is equal to its ranking, and x meet z is equal to y meet z, then x is equal to y. If you plug in, so if you plug in A, B, and C here, right, A join C is 1. Okay, if C is equal to rho of C, and x join as A meet Z, A meet C is 0, and B meet C is 0, then this would say that x has to be equal to y. But that's not true for the pentagon. This is, you know, you get a contradiction there for the pentagon. So if rho of C is C, then you contradict the Geifman condition. So erase that. So then rho of C must be 1. The Blast condition says that if two elements have the same ranking, then they have the same ranking as their meet, right? And so if rho of B is equal to rho of C, and they're both 1, then rho of C and rho of C meet B, which is 0, has to be 1. And so this, in this case, the extension will be cofinal. Okay. So this is possible, right? It could be that rho of C is 1, rho of B is 1, rho of everything is 1, and so the rank set is just 1. That's just a cofinal extension. What if that doesn't happen? What if it's not a cofinal extension? Well, if that doesn't happen, then rho of B is not going to be equal to rho of 1. It must be the case that rho of B is equal to itself. Okay. Why is that? If you go back to the lattice and you look at this picture, the rank has to be at least itself. So if it's not 1, it's going to be itself. It's going to be B. And okay, so then there's that. The next thing that we know, and this one I won't prove, but this is in the book, theorem 4.6.1 of structures of structure of models of Peano arithmetic. Rho of 0 is not equal to B. This is an interesting short proof, but I'm not gonna go through it. And so the possible rank sets are, if you put all this together, it could just be 1, and you get a cofinal extension. It could be 0, B, and 1, and in which, so if 0 is in the rank set, then you get an end extension. Excuse me. It could be 0, A, B, and 1, which would give you an end extension, or it could be A, B, and 1, which would give you a mixed extension. And so this is not doing any. This is just looking at the rank, the properties we know about ranks, and this one result that says rho of 0 is not B. So in this case, could rho of 0 be A? Right? Can we get a mixed extension? And so this is the result. This last one is ruled out by a recent paper of Jim's. That's in JSL. So I'm not gonna, again, I'm gonna just mention it. I'm not going to go into the details of how it's proved. It's a very interesting paper. So I'll say that I'll say that, and I'll leave it open for if anyone wishes to ask about it, because Jim's here. And so can these all be realized? This one can be realized. This one can be realized, and this one can be realized, but this one cannot be realized. Number 4 cannot be. And so the result, let's say an extension is mixed, as Roman mentioned. If the extension is neither an end extension nor a cofinal extension. And okay, so some summary of results. Wilkie proved that the that the pentagon can be realized as an end extension. And I believe that his paper specifically looked at the standard model, but it's pretty easy to kind of to generalize his work to get every countable M has an elementary end extension where the interstructure lattice is N5. And if I remember correctly, it was this version. It was this ranking, where A was cofinal and B. Jim, in his paper that introduced the CPP representations, basically proved that whenever you have a model, a countable non-standard model of PA that has any elementary extension that realizes a particular lattice, a finite lattice, then that lattice can be realized in a cofinal extension. And so you can apply this to the pentagon to show that there is a cofinal extension that realizes a pentagon. And then in this recent paper that Jim showed that no mixed extension can be realized as the pentagon lattice cannot be realized as a mixed extension, and that ruled out that other case. But there was a very interesting result at the end of that paper as well that said that this result 3 does not generalize to models of PA star. Okay, so the result says every countable recursively saturated model M has an expansion to a model of PA star, which means an expansion in a countable language that satisfies induction in that expanded language, for which there is an elementary extension whose interstructure lattice is N5, but that elementary extension is a mixed extension. Okay, and that was a very, very surprising result, because almost every, as far as I know, every other result in this realm for models of PA generalized to models of PA star. And Jim and Roman can correct me if there are others that you know of, because that was very surprising to me to see that this result that says, okay, the pentagon cannot be realized as the interstructure lattice of models of PA does not generalize to models of PA star. Is there something else like that where it doesn't generalize to PA star? Not that I can think of, but again, I'll let Roman and Jim.
I thought, Jim, is there some stronger assumption than just recursive saturation?
I'd have to double check the paper again, but
was it like super recursive saturation? There was something more than
the expansion ends up being super.
I see. So you start with any recursive saturated, then you expand to this to something that's super. I see.
Yeah. So I'm not going to go through this, but I'll just mention this was the representation of N5 that Wilkie used in his paper. That again, I mentioned we could realize this rank set. I'm not going to say anything about this one. This one is ruled out, number 4, for the case of PA. And the ranking starts very similarly, right, as B2, because it's sort of N5 looks a lot like B2 in some way, right? There's A here and there's C here, and if you forget about this B here, then it's essentially B2, and so you have the ranking on B2, and then you split the alpha of A classes in a very particular way. And so this is the representation that Wilkie uses. Jim generalizes this a little bit in the book. There's a section in the book that's dedicated to this, to proving essentially this theorem. But this was a sort of from the original proof. Okay, so I'll stop here and take questions if there are any. I presume that there are some, but that's all I have prepared for right now. So thank you.
Okay, thank you, Athar. So since I'm officially sort of chairing this session, it's time for our reaction. So let's thank Athar. Thank you very much. It was a very nice, clear talk. I have just one quick thing about the last slide, because I don't remember, and I used last time I was here, I had Mills's paper with me, but I don't have it here anymore. At Mills, let's take a look at this at the picture of the N5. So you get N5 by doubling this sort of. You have B2.
You cannot double.
Right, and then so this AB, you just took one point from B2 and just split it. And then I remember that in the introduction, Wilkie in his paper has something about this general procedure when you start with the B2 and replace A by a finite lattice, maybe finite distributive lattice, and you replace B by some finite lattice, and there is some general about that. I don't remember now. Maybe you or Jim. Jim, do you remember what it was?
So, Roman, can you repeat that question?
So the question is that it seemed to me that the introduction in Wilkie's paper, there is something about this general situation. Then you start with B2, and you have A, and you replace A by some finite lattice D1, and you replace B by some other finite lattice D2. And he had something to say about this particular lattice.
Yeah, I don't know right now.
Yeah, well, it's a pity I don't have it with me here.
It sounds right. Yeah,
because I remember this picture so it must have been for something there.
I have to find that paper. It's been I can't. I don't have the paper open. I have to find it again.
And another question, as I remember, because I was giving a talk on the lattice problem some time ago in Warsaw, and somebody asked me about N5.
But N5?
Where is this notation from? What is N6?
N means non-modular. Now where is the notation from? But the M's, so the M's are modular lattices and the N's are non-modular lattices.
But then I looked it up. I remember that there was this, that there is some hierarchy of those M's.
Yeah. So the Mn are modular non-distributive lattices, and the N's are non-modular lattices. And so I guess this is the simplest.
N5 is the simplest.
N5 is the simplest non-modular lattice. Yeah. Modularity is some sort of weak form of distributivity. I can't remember the exact, but it's a weak form of distributivity. So every distributive lattice is modular, but it's not equivalent. Ken has his hand, so I'll take Ken's question.
Yeah, it's a general kind of question. Now, here, this is a very rich and deep and complex analysis going on here. But the question is, are there other theories for which this kind of analysis has been made or is being made, like real close fields or something? Or is there something special about PA that lends itself to this kind of model theoretic and numerical analysis?
Right. So this was asked a couple weeks ago. I think Lori asked the same kind of question a couple weeks ago about can this
great minds think alike.
Yeah, exactly. And I don't have a satisfying answer to it, but maybe Jim could say something. But I think in other theories, we don't necessarily know if the problem is if the interstructures are a lattice, if the substructures
Right,
form a
I think
lattice.
that's that is a problem, yeah, right there, yeah.
Oh, that's a simple answer.
No, that's right. And I think Jim, knows the problem intricately. And I mentioned that he also has a paper, the JAF proceedings from 3 years ago in New York, when he looks at this sort of parallel problem for what are they called? Narrowed something semi-rings, which are sub-rings of models of a fragment of arithmetic, where something similar works because of some special features of those structures. But other than that, for example, here Athar mentioned Blas condition and Geiger's condition. They're extremely specific to models of PA. And the fact that you have single column closures that behave in certain ways that is somewhat understood, that somehow hangs heavily over this whole theory. So there is no other theory. I know, certainly not fragments of PA. They wouldn't. There was a very interesting talk in the fall by Sun Mangju. So he and Tin Lok Wong, they look at this phenomenon that a cofinite extension of a model of I sigma n doesn't have to be elementary. But there are some traces of elementarity, and there is some very specific model theory that's connected to definability of initial segments in the theory. But then so one could consider something like substructures of models of I sigma n, but it gets incredibly messy.
Mm-hmm. Thank you.
Yeah, I mean, as far as I know, all the techniques we use, we use kind of everything we use, we know we uses the basic results of models of PA, that we have access to definable Skolem functions and stuff like that, for example. And these things can we do without them? Maybe, but I like to say that you have a lattice, right? To say that we have joins, right? I guess I should joins are that we use Skolem closures to say that, and so I don't know. Maybe there's some general result about if a theory has definable Skolem functions, and I don't know, something else.
We could ask Kirby if these results apply nicely, say, to set theoretical formulations of arithmetic.
That was his question.
This was actually Laurie's question.
Yeah, that was his question.
2 weeks ago.
Yeah.
No, but I mentioned also that all of it stems. The early results are from Haim, who's not here today. Maybe he could have said something about it. And he has this monumental paper, 80 pages on models and types of Peano arithmetic, when he gets this uniform procedure for constructing end extensions and minimal extensions, and using minimal types and extensional types that we later called indiscernible types. And this whole machinery exists, and he proved basic results about these lattices using this technique. And then this was in 1970s. The paper was from 1976, but he announced those results in 1965 in an abstract in the American Mathematical Society. There is an abstract session. They used to publish abstracts. So all the results were there, and Shelah got interested. He asked exactly this question, how general model theoretic are these results about the particular forms of extensions? And it's an interesting paper that he came up with. And he could only, under some assumptions about existence of special types of Skolem functions and some other model theoretic assumptions, he could reproduce end extensional types. But for what is done here, at least for Haim's results about distributed lattices, one needs minimal types, and that could not be reproduced in another setting, a more general setting. It seems like one needs PA or PA star, but nothing less than that.
So it would
Wow.
maybe look in ZF plus V equals L or something.
Right. Ali certainly has tried.
Mm.
And so there are all kinds of this whole, you would know, Zach, there's this whole, technique of transferring results from PA to ZF, with additional assumptions. But Geisman, Geisman has another paper that, that's actually what Ali uses for various proofs, not Geisman minimal types, but certain ultra product constructions, definable ultra products that can be iterated, which is some kind of equivalent, say, of saying something here, some Ramsey properties that you need. So you have those Ramsey properties in PA, but you don't have them in weaker theories. And not to mention that I didn't mention, Jim should give us a talk once. Jim, you can talk about anything you like. You don't need to give us any proofs. Just make a list of results, because Jim uses very non-trivial combinatorics to prove these results. All kinds of fancy combinatorial theorems that then apparently are formalizable in PA or fragment, and then they are used to, those canonical partition properties. So these are not very non-trivial facts that you need to know that they are somehow formalizable in PA.
Yeah.
So it's hard to see how to transfer it to any other setting.
Wow. Right.
Yeah, so in all of these in all of these results, we didn't mention essentially one of the main techniques which Jim uses to prove certain classes of lattices can be realized as substructure lattices. One of those main techniques is to try and find an algebra for which this lattice can be represented as a congruence algebra. Not going to say anything about that other than if you know what a congruence lattice is, and you do some work. Jim did quite a bit of work on these and used some results about combinatorics that showed that these representations can these representations can essentially you can get larger and larger in terms of the amount of this how high a CPP representation you get. Now you can get larger and larger representations that satisfy more and more sort of of these canonical partition properties that you want, that will, as long as you start with some congruence representation. And so any lattice that has a congruence representation can be realized as a substructure lattice. And as far as I can tell, I think every lattice that we know, right, is that the case? If every lattice that we know can be realized as a substructure lattice has a congruence representation.
Right. That's right. But it's a congruence lattice of a finite algebra.
Of a finite algebra, yes. And so that so when Roman mentions these like non-trivial combinatorics, there's a lot of non-trivial combinatorics in going from you have a congruence lattice to then you have a representation that satisfies more and more of sort of these kind of, I have to go all the way back to the beginning, these canonical partition properties that you want, right? Like you'll get a higher n for you can increase the n there for if it's a congruence allows, and these involve these theorems of like the Hales-Jewett theorem and Hummel-Voigt theorem, like these theorems from combinatorics that are really quite interesting, but I don't know if there's any other setting that you can. I mean, presumably, I mean, yeah, I don't know. I don't know what you could say about it in set theory. Presumably, you can say something about it in set theory, but I don't know. And then to go from we have an n CPP representation for every n to then say we have an elementary extension that realizes this lattice. It uses overspill, right? And then uses overspill to then build a cofinal extension at that point. So I don't know, it's an interesting question. I think this is something that I'm sure someone has thought about, and I'm sure Ali probably has thought about. Maybe something to ask him of which of these notions can generalize to set theory. I would suspect we would need different techniques entirely. Yeah. But I shouldn't speak out of turn here because the expert is here, so I can defer to Jim on if you know anything about how any of these could possibly generalize to set theory. I don't know. I mean, do you have any intuition?
So I missed what you're asking.
If you assume, I think what Zach was asking, if you assume ZF and V equals L, if your model of that,
Oh, right.
can some of these techniques be recovered, and therefore can you?
I
find
would think you would need more than that. So, like I don't know, the model looks like it's a model of a weakly compact cardinal or something like that, or Ramsey cardinal.
Yeah.
To drive the combinatorics.
Yeah, I would think.
Yeah.
Yeah.
That's a good question. I think even if there's not a satisfying answer to that, it may be interesting to think about of why there's not a satisfying way to translate this. Like, what there might be something to say. Other questions or?
Oh no, this is my time to ask.
Sorry.
Other questions?
Nope.
So if there are no other questions, thank you, Athar, for a great talk. Let's thank Athar and keep an eye on announcements. So we will have at least one more MOPA talk and perhaps some more in the future. But this all will be announced soon.
Okay.
Thank you.
Thanks, Athar.
Thank you, Jim.